Hello everyone. Today we're going to talk about Fourier transform and its applications. So, without much further delay, let's start. So, an introduction about what Fourier transform is. So, the Fourier transform is a mathematical operation that transforms a function of time into a function of frequency. It decomposes a signal into its constituent frequencies, allowing us to analyze the frequency components of signals. Converts time domain signals into frequency domain representations. So this is the mathematical representation of the Fourier transform. And f of t is the original signal, omega is the angular frequency, and this is the complex exponential function. And as you know, I is the imaginary unit. And capital F of omega is the Fourier transform of the original signal. Continuous and discrete Fourier transform. So definition, the CFT, which is continuous Fourier transform, is used for continuous signals. It transforms a continuous time domain signal f of t into a continuous frequency domain representation. And definition, the DFT, which is the discrete Fourier transform, it is typically those sampled at regular intervals, transforms a finite sequence of equal spaced samples x of n into a discrete frequency representation x of t. So basically, Fourier transform is of two types, continuous and discrete. As you know, continuous signals are the signals which can be depicted or uh, represented at any point of time, whereas discrete signals are predicted or plotted only at integral levels. So these are the examples of continuous signals. These are the examples of discrete signals or discrete Fourier transforms. And basically, Fourier transforms are uh, displayed in frequency domains. So key properties, it's linearity, time shifting, frequency shifting, and convolution. Application of signal processing. So before going into this, we need not go into depth for about the properties right now, but these are one of the most used and applied properties by the Fourier transforms: frequency shifting, convolution, time shifting, and linearity. As we move further, we'll know what these properties are in depth. Application in signal processing. So audio processing, noise reduction, equalization, filtering. Noise can be identified in the frequency domain and removed or reduced using filters designed to target specific frequency ranges, improving the overall clarity of the audio signal. Denoising. By transforming audio into the frequency domain, it becomes easier to identify and remove unwanted noise without significantly affecting the desired audio content. Image processing. Transform Transform coding. The Fourier transform can help compress images by transforming them into the frequency domain, where less important high frequency components can be discarded or quantized more aggressively. Example, JPG uses the discrete cosine transform. A related technique, inverse transform. After processing an image in the in the frequency domain, example filtering, the inverse Fourier transform can be used to convert it back into the spatial domain. Frequency analysis. Edges in images correspond to high frequency components. By analyzing these frequencies, edge detection algorithms can be implemented more effectively. Feature extraction. The Fourier transform can help extract features from images for tasks like object recognition and classification by analyzing the frequency characteristics. So, as you know that there are many more applications, but the major applications of Fourier transforms are image processing and audio processing, or basically the receiving and transmitting of digital data. And coming back to key properties, time shifting is the shifting of the signal from one time to another time. Basically, let's say the time signal domain or the signal ranges from time 2 to 4 seconds. Then time shift changes this range from 4 to 6 or 6 to 8. It depends on the property of the time shifting. And basically linearity frequency shifting. So these actually change the position and the way the signal is transmitted. So that's it for this video. Thank you.